On December 26th, the interstellar object 3I Atlas was reported to have lost up to 99% of its mass in a short period of time without leaving behind any debris or signs of an explosion. Previously, the stability of its orbit led scientists to believe that 3I Atlas was a massive block of ice weighing approximately 33 trillion kilograms, but new measurements from the James Webb Space Telescope indicate that it is much smaller and lighter, creating a mathematical paradox that is difficult to explain. From this contradiction, two main hypotheses have emerged. Either 3I Atlas is a fluffy comet with an extremely fragile structure, or it is an artificial construct such as a hollow shell or a light sail capable of self-adjusting its properties to camouflage itself and move through space. At the same time, some analyses suggest that 3I Atlas may not simply be a natural rock, but an artificial transportation system carrying out a data collection mission, with Professor Avi Loeb proposing the idea of using such objects to send messages or even human genetic material into deep space at speeds far beyond current technology. However, newly observed self-acceleration and the release of unusual fragments have also raised concerns about possible biological surveillance or the presence of unmanned devices penetrating Earth's atmosphere, making the close approach of 3I Atlas to Jupiter in March 2026 a pivotal moment, one that could force humanity to choose between defensive action or attempting to connect with a much larger galactic network. What these new discoveries reveal about Atlas is what we will explore next. The silence surrounding 3 Atlas was not an absence of information, but a presence so heavy that it shaped every early assumption scientists made about the object. For months, 3 Atlas moved through interstellar space and into the inner solar system without the slightest measurable deviation, a behaviour that quietly suggested mass density and inertia far beyond what the eye could see. When astronomers tracked 3 Atlas across the sky with extraordinary precision, the lack of wobble became a signal in itself because in physics, silence under pressure often implies weight. Radiation from the sun pushed relentlessly outward, yet 3 Atlas did not flinch, did not drift, and did not betray the subtle accelerations that even modest cometary bodies usually display. Based on that stillness, researchers inferred that 3 Atlas must be enormous, because only a massive object could absorb so much force without responding. In this early phase, 3 Atlas was framed as a giant, a solid mountain of ice and dust several kilometers wide, drifting with the confidence of something too heavy to be disturbed. More than 200 observatories contributed data, and all of them told the same quiet story about 3I Atlas. The trajectory of 3I Atlas followed gravity with near-perfect obedience, as if the object were a dead weight rather than an active traveller. This consistency gave rise to a comforting narrative, because a heavy object behaving predictably fits well within existing models of interstellar debris. Yet beneath that comfort lay an unresolved tension, because silence can also be deliberate rather than passive. Some scientists began to ask whether 3 Atlas was truly inert, or whether its stillness was masking something more complex beneath the surface. If 3 Atlas were venting material in subtle or asymmetric ways, the absence of motion would require an explanation that mass alone could not provide. As the months passed, the silence of 3 Atlas became more suspicious than reassuring. The object absorbed solar influence without responding, and that resistance invited a deeper question about whether 3I Atlas was simply heavy, or whether it was controlling how it interacted with its environment. At this stage, no claims were made about artificiality, but the groundwork was laid for doubt because nature rarely maintains perfect balance without cost. The early portrait of 3 Atlas as a colossal unresponsive body would later become a reference point, not because it was proven correct, but because it defined what would eventually collapse. In hindsight, the silence of 3 Atlas was not the end of the story, but the opening move in a much larger puzzle. Inertia became the invisible ruler by which scientists measured 3 Atlas long before they understood what 3 Atlas truly was. When solar radiation pressed outward with a constant force, the expectation was simple, because light objects yield and heavy objects resist, and 3I Atlas resisted with unsettling consistency. From that resistance emerged the first major assumption, because if 3I Atlas did not accelerate, then 3I Atlas had to possess enormous mass. The calculations followed familiar ground, relying on radiation pressure models refined over decades of cometary observation. Sunlight carries momentum, and when it strikes a body releasing gas or dust, that momentum translates into measurable motion. Yet 3 Atlas showed none of the expected signatures even when observational sensitivity reached levels capable of detecting shifts smaller than a fraction of an arcsecond. This absence of acceleration pushed researchers toward a singular conclusion, because inertia does not lie unless something interferes with how it is measured. To remain so steady, 3 Atlas was modelled as a multi-kilometre object with tens of trillions of kilograms locked into its structure. In this framework, 3 Atlas became a silent giant, a body whose mass alone explained its indifference to solar influence. But the anomaly crept in quietly because inertia can be genuine without being simple. If 3I at last were releasing material in directions that cancelled out net acceleration, then apparent mass could be an illusion rather than a fact. This possibility sat uncomfortably at the edge of the data because it required behaviour more coordinated than most natural bodies exhibit. 3 Atlas forced astronomers into a narrow corridor of interpretation, where either the object was unimaginably massive or the models themselves were incomplete. Radiation pressure did its work openly, yet 3 Atlas absorbed that pressure without consequence, creating a paradox that could not be resolved by observation alone. At this stage, the scientific community leaned toward mass not because it was elegant, but because it was the least disruptive explanation. Emotion entered the analysis not as fear but as unease, because something about 3 at last felt too balanced, too well behaved for an interstellar wanderer. The numbers made sense individually, yet together they formed a picture that relied heavily on assumption rather than confirmation. This dependence on inferred mass would later become a fragile pillar, because when inertia is reinterpreted, the entire structure above it begins to sway. Thus, the story of 3 at last moved forward, carrying an invisible weight, preparing the ground for a moment when radiation motion and mass would no longer agree. When James Webb turned its instruments toward 3 Atlas, the calm certainty built on inertia began to face a new kind of measurement, because James Webb did not merely track where 3 Atlas was, but how 3 Atlas was being nudged. The key detail was not dramatic at first, because the non-gravitational acceleration detected around 3 Atlas was small, almost a whisper layered onto the dominant pull of the Sun. Yet that whisper mattered, because any extra push implies a source, and for comet-like bodies, the source is usually outgassing a steady leak of molecules accelerated into space. Scientists took the measured acceleration of 3 Atlas and asked a ruthless question, because physics does not accept a story unless the numbers agree. If 3 Atlas was venting gas at a certain speed, and if 3 Atlas was losing mass at a certain rate, then the reaction force could be computed, and the mass of 3 Atlas could be inferred from how strongly the object responded. This is where the James Webb calculation became a scalpel, because the same motion that was once interpreted as evidence of a massive body could now be interpreted as evidence of a far lighter one. The models constrained by the acceleration data pushed 3 Atlas into a smaller size regime, shrinking the imagined nucleus to roughly a kilometre rather than several. With that reduction, the inferred mass of 3 Atlas collapsed by orders of magnitude, transforming 3 Atlas from a mountain into something closer to a shell. The shift was not presented as certainty, because every inference depends on assumptions about jet geometry, gas composition, and how evenly the activity is distributed across 3 Atlas. Still, the anomaly could not be ignored because the discrepancy between the earlier inertia-based mass and the James Webb-based mass was too large to dismiss as a trivial adjustment. If 3 Atlas was truly light enough to be pushed measurably by outgassing now, then 3 Atlas should have been susceptible to solar pressure earlier, and the long months of perfect stability would need a new explanation. Alternatively, if 3 Atlas had been heavy before, then 3 Atlas would have had to change in a way that preserved structure while losing vast amounts of material without leaving a visible debris signature. Emotions surfaced again as controlled discomfort, because the data did not scream chaos, but it quietly undermined the foundation of what had seemed obvious. James Webb did not reveal a spectacular flare, yet James Webb forced a reconsideration of what 3 Atlas might be, because a small non-gravitational push can expose a large hidden truth. From this point forward, 3 Atlas could no longer be described only by where it travelled, because 3 Atlas had begun to reveal how it responded, and that response opened the door to deeper contradictions. The paradox surrounding the apparent loss of mass from 3 Atlas did not announce itself with violence or spectacle, because there was no explosion, no expanding cloud, and no trail of fragments marking a catastrophic breakup. Instead, 3I Atlas appeared to transition from an inferred giant into a far lighter body, while remaining visually coherent, a transformation that defied the usual signatures of physical destruction. In ordinary cometary physics, losing even a small fraction of mass tends to be messy, because material separates, spreads and leaves behind observable structures. What made the case of 3 at last so unsettling was that nearly all indicators of such disruption were absent. If 3 at last had truly shed 99% of its mass, the surrounding space should have been filled with dust, ice or debris reflecting sunlight and betraying the event. Yet telescopes found no expanding shell, no dense tail consistent with sudden disintegration, and no residual fragments moving independently from 3 Atlas. This absence created a contradiction that could not be smoothed over with observational uncertainty alone. Either 3 Atlas had lost an extraordinary amount of mass without releasing it into the surrounding environment, or 3 Atlas had never possessed that mass in the first place. Both options strained conventional models because matter does not simply vanish, and miscalculations rarely persist across independent measurement techniques. Some researchers suggested that the mass loss of 3 Atlas could have occurred gradually and directionally, with material escaping in a narrow flow that evaded detection. However, sustaining such a process while preserving the apparent shape and brightness of 3 Atlas would require a level of consistency that natural outgassing rarely achieves. Others propose that 3 Atlas might be composed of extremely low-density material where large apparent size does not correspond to large mass. That explanation reduced the severity of the paradox, but it introduced another layer of unease because a structure that large and that light would behave very differently under stress. If 3 Atlas were truly fragile, the thermal and mechanical forces near the Sun should have torn it apart, yet 3 Atlas remained intact. The object held together while the numbers describing it fell apart, and that inversion of expectation became impossible to ignore. Emotionally, the situation invited restraint rather than panic, because the data did not point to immediate danger, only to conceptual failure. 3 Atlas stood at the center of that failure not as a threat, but as a reminder that disappearance without evidence challenges the way mass, motion and structure are usually linked. By the time this paradox was fully acknowledged, 3 Atlas had already shifted from being a heavy certainty into a question shaped by what was missing rather than what was seen. As conventional explanations strained under the weight of contradiction, the hollow shell hypothesis emerged not as a declaration, but as a quiet attempt to reconcile what 3 Atlas was doing with what physics allows matter to do. The idea proposes that 3 Atlas may not be a solid body at all, but a structure whose apparent size vastly exceeds its true mass, creating the illusion of substance without the burden of density. In such a configuration, 3 Atlas could present a large cross-section to observers while remaining light enough to respond selectively to external forces. This concept gains relevance when radiation pressure is reconsidered not as noise but as a tool. A thin extended structure interacting with sunlight can experience forces that mimic natural outgassing, yet originate from pure momentum exchange rather than material loss. If 3 Atlas possessed a surface optimized to absorb or reflect stellar radiation, then subtle accelerations could be produced without the violent signatures expected from a crumbling comet. The light sail hypothesis extends this reasoning into a more speculative domain, where geometry replaces mass as the dominant variable. In this scenario, 3 Atlas would not need engines or fuel in the conventional sense because the star itself would become the propulsion system. By altering orientation or surface properties, 3 Atlas could modulate how radiation pressure acts upon it, remaining inert when desired and responsive when conditions align. What makes this hypothesis difficult to dismiss outright is that it addresses multiple inconsistencies at once. A hollow or sail-like structure would explain why 3 Atlas appeared massive during early observations, while later behaving as a much lighter object. It would also account for the absence of debris because there would be little bulk material to disperse in the first place. Still, the hollow shell idea rests on uncomfortable ground because it assumes a level of structural coherence uncommon in natural interstellar debris. Nature produces porous objects, but it rarely produces thin, resilient shells on kilometre scales that survive thermal stress without fragmentation. For 3 Atlas to maintain such integrity, the material properties involved would need to exceed what is typically observed in cometary nuclei. Emotionally, this hypothesis shifts the tone of the discussion because it replaces accidental erosion with intentional design-like behaviour without asserting intent. 3. Atlas viewed through this lens becomes less a dying remnant and more a system interacting purposefully with its environment. Whether 3A at last is natural or artificial remains unresolved, but the hollow shell hypothesis marks a turning point where absence of mass becomes an explanation rather than a problem. The idea of camouflage becomes relevant when 3A at last is considered not only as a physical object, but as a participant in an environment shaped by expectation. Interstellar space is filled with debris, and astronomers are trained to classify unfamiliar visitors by comparing them to comets, because comets provide a familiar template for motion brightness and behaviour. By resembling a comet, 3I Atlas would naturally be interpreted through that template, allowing assumptions to form before deeper questions are asked. A comet-like appearance does not require a solid cometary interior, because gas dust and reflected light can create convincing signatures even when the underlying structure is unusual. If 3 Atlas possessed a surface capable of releasing or interacting with material in limited ways, then the presence of a coma or tail would not necessarily indicate a traditional nucleus beneath it. In this framework, 3 Atlas does not need to deceive actively, because existing classification habits perform the work automatically. The effectiveness of such camouflage lies in timing and context rather than complexity. Early in its journey, 3 Atlas appeared distant, cold and quiet, matching expectations for an inert interstellar object entering the solar system. Later, as 3 Atlas approached the Sun, subtle activity emerged, reinforcing the cometary narrative just enough to prevent immediate reclassification. What makes this pattern unsettling is how efficiently it aligns with human observational bias. Astronomers expect interstellar visitors to behave like comets, so evidence consistent with that expectation carries disproportionate weight. 3I Atlas, by fitting within that expectation, while quietly violating key physical relationships, occupies a space where contradiction is slow to register. Camouflage in this sense does not imply intent, but it does imply compatibility between behaviour and interpretation. A natural process could in principle produce a body that mimics cometary features while possessing an unconventional internal structure. At the same time, 3 Atlas demonstrates that such mimicry can persist across multiple observational platforms without triggering immediate alarm. Emotionally, this realization introduces a softer but deeper form of unease, because it suggests that misinterpretation can occur without error or negligence. 3 Atlas was not overlooked or ignored, but carefully studied and still misunderstood, at least in part. The object passed through layers of scrutiny while maintaining an identity that felt complete enough to resist challenge. As Chapter 1 draws to a close, 3 Atlas stands defined less by what it has revealed than by how smoothly it blended into expectation. Whether 3 Atlas is a rare natural anomaly, or something more structured, the possibility of comet-like camouflage reframes the earlier silence as strategy rather than absence. From this point forward, 3 Atlas cannot be examined only as an object in motion, because 3 Atlas has demonstrated how easily appearance can shape belief in the vast quiet of interstellar space. When the JUICE spacecraft observed renewed activity around 3 Atlas, the data introduced a stabilizing counterweight to the growing unease surrounding the object. Unlike distant telescopes that inferred behavior indirectly, JUICE captured close-range evidence that 3 Atlas was actively interacting with solar energy in ways consistent with known cometary physics. This observation mattered because JUICE was not designed to hunt anomalies yet. 3 Atlas appeared clearly within its instruments as an object shedding material in response to heat. The images returned by JUICE revealed a compact coma enveloping 3 Atlas, along with distinct structural features that immediately drew comparisons to familiar solar system comets. In particular, JUICE identified two separate tails associated with 3 Atlas, one aligned with the solar wind and another tracing the object's orbital path. These features suggested ionized gas and dust behaving under electromagnetic and gravitational forces, reinforcing the idea that 3 Atlas was undergoing natural sublimation. For scientists seeking grounding, this moment provided relief, because 3 Atlas finally behaved in a way that fit established models. The plasma tail indicated interaction with charged particles streaming from the Sun, while the dust tail implied solid material escaping from the surface of 3 Atlas. Such behaviour has been observed countless times in comets formed within the solar system, lending credibility to the interpretation that 3 Atlas was not fundamentally exotic. Yet even as the evidence supported a natural explanation, the context surrounding 3 Atlas complicated its meaning. JUICE observed activity only after 3 Atlas had already passed through months of unexplained inertia, a sequence that felt reversed compared to typical cometary evolution. This raised questions about whether 3A at last had always possessed volatile material or whether the activity was triggered by a specific thermal threshold. The timing of JUICE's observations became central to interpretation, because 3A at last displayed textbook cometry features precisely when scrutiny was intensifying. If 3A at last were an ordinary interstellar comet, the JUICE data would simply confirm expectations and close the case. However, because 3A at last had already violated assumptions about mass and motion, the same evidence carried an undercurrent of doubt. Emotionally, the JUICE results softened the narrative without resolving it. 3A at last appeared less threatening and more familiar, yet familiarity itself became suspect in light of earlier contradictions. Rather than restoring certainty, JUICE reframed 3 at last as an object capable of behaving naturally while remaining structurally ambiguous. As the analysis moved forward, 3 at last stood at an uneasy intersection between confirmation and confusion. The activity observed by JUICE anchored 3 at last firmly within known physics, yet it also intensified the question of how much of that behaviour reflected surface expression rather than internal reality. The presence of 2 distinct tails extending from 3 at last introduced a visual language that astronomers have learned to trust, because plasma and dust tails are among the most familiar signatures of cometary activity. In the images associated with 3 at last, one tail aligned sharply away from the Sun shaped by the solar wind, while the second followed the object's orbital path, tracing a slower, heavier flow of material. This dual structure placed 3 at last squarely within the visual taxonomy of comets, where charged particles and solid grains separate under different forces. The plasma tail of 3 at last responded directly to the magnetic environment of the Sun bending and stretching, in ways governed by electromagnetic fields rather than gravity. Such behaviour implies ionized gas stripped of electrons and carried outward at high speed, a process that occurs naturally when volatile compounds are heated and dissociated. For observers, this aspect of 3 at last reinforced the idea that the object was shedding material in a conventional way consistent with long-studied physical mechanisms. At the same time, the dust tail of 3 at last told a slower story. Dust particles heavier and less responsive to magnetic forces spread along the orbital track, forming a luminous trail shaped by radiation pressure and gravity together. The coexistence of these 2 tails suggested that 3 at last was releasing both gas and solid material, a combination that aligns well with classical comet models. Yet the anomaly re-emerged when scale and persistence were considered alongside structure. For an object inferred to be only about a kilometre across, the sustained production of both plasma and dust raised questions about internal supply and mechanical resilience. 3 at last appeared able to feed both tails without visible depletion, fragmentation or collapse, which is unusual for a body operating near the lower bounds of structural mass. The geometry of the tails also introduced subtle tension into the interpretation. If the material released from 3 at last were entirely random variations in tail intensity and direction would be expected over time. Instead, the overall morphology remained coherent, suggesting a stability in how 3 at last interacted with solar forces. Emotionally, the twin tails created a sense of reassurance layered over uncertainty. 3 at last looked like what astronomers expected to see. An expectation carries comfort even when underlying questions remain unresolved. However, familiarity can mask complexity, and in the case of 3 at last, the very normality of the plasma and dust tails deepened the puzzle rather than resolving it. As this section closes, 3 at last stands illuminated by its own emissions, displaying features that argue strongly for a natural process while quietly refusing to explain how such behaviour is sustained. The estimate that placed the nucleus of 3 at last at roughly 1 kilometre in diameter introduced a paradox that refused to stay theoretical. A body of that size, when exposed to sustained solar heating, is expected to experience structural stress that accumulates rapidly, especially when gas and dust are vented from beneath its surface. In known comets, even larger nuclei often fracture, split or shed chunks when internal pressure exceeds material strength. Yet 3 at last showed no such signs. As observations continued, 3 at last maintained coherence despite releasing enough material to support a visible coma and 2 persistent tails. This behaviour forced scientists to confront an uncomfortable mismatch between size and durability, because a 1 kilometre object should not remain intact while behaving so energetically. If 3 at last were composed of loosely bound ice and dust, internal voids and fractures should have propagated under thermal cycling. The stability of 3A at last suggested either an unusually strong internal structure or a process that distributed stress in a highly controlled manner. In natural terms that would require material properties rarely observed in cometary bodies, such as tensile strength, far exceeding that of porous ice aggregates. 3A at last therefore occupied a narrow space where it appeared small enough to be fragile yet resilient enough to resist collapse. Attempts to reconcile this contradiction often return to geometry and composition. If 3A at last were not a solid sphere but a layered or shell-like structure, then internal pressure from outgassing could be redirected rather than concentrated. Such a configuration would allow 3I at last to vent material while preserving its overall shape, reducing the likelihood of catastrophic breakup. However, this explanation carried its own implications, because shell-like resilience on kilometre scales challenges expectations about how interstellar objects form naturally. 3I at last would need to survive not only solar heating but also the mechanical stresses of ejection from its original star system and prolonged exposure to cosmic radiation. That survival history adds weight to the idea that 3I at last is not merely unusual, but optimized for endurance. Emotionally, the intact nucleus of 3I at last produced a quiet form of tension rather than alarm. The object did not behave aggressively or unpredictably, yet its refusal to fracture undermined confidence in simple models. 3I at last remained whole when it should have broken, and that persistence forced observers to consider whether strength, rather than mass, was the defining characteristic. By the end of this phase of analysis, 3 Atlas stood as an object whose integrity spoke louder than its emissions. The paradox of a 1-kilometre nucleus that does not break did not demand immediate answers, but it ensured that every subsequent interpretation would be shaped by what 3 Atlas managed to endure. The question of whether the observed activity around 3 Atlas arises from sublimation or from something closer to technological exhaust sits at the centre of the object's ambiguity. Sublimation is a familiar process because when ice warms in a vacuum, molecules escape and generate jets that push against the remaining mass. For 3 Atlas, this explanation initially appears sufficient because the presence of gas and dust aligns with expectations for a heated comet. However, the details complicate that comfort because sublimation usually produces uneven forces that lead to rotation changes, fragmentation, or erratic acceleration. 3I. Atlas, by contrast, has displayed a remarkably smooth response to solar heating with non-gravitational acceleration that remains stable over time. Such stability suggests that whatever is driving the motion of 3 Atlas operates within narrow tolerances rather than chaotic release. When models attempt to reproduce this behavior using sublimation alone, they must assume finely tuned jet distributions. For 3 Atlas, those jets would need to activate symmetrically and persistently, cancelling torque while still producing thrust. Natural comets rarely maintain such balance for long, especially when their internal structures are weak and heterogeneous. This is where the exhaust hypothesis enters cautiously, not as an assertion, but as an alternative frame. If material escaping from 3 Atlas were part of a controlled process rather than random sublimation, then consistency would be a feature rather than an anomaly. In that scenario, the gas surrounding 3 Atlas would not be waste in the geological sense, but a byproduct of regulation or propulsion. The idea becomes more compelling when energy efficiency is considered. A technological system interacting with stellar radiation could use minimal mass loss to achieve measurable changes in trajectory. 3 Atlas would not need to burn fuel aggressively because the sun itself provides a continuous external energy source. Emotionally, this comparison shifts the discussion from erosion to intention without crossing into certainty. 3 Atlas does not behave like an engine firing in bursts yet. 3 Atlas also does not resemble a fragile ice body slowly tearing itself apart. The activity sits in between calm and persistent, as though designed to avoid extremes. From a distance, sublimation and exhaust can look deceptively similar because both produce gas dust and acceleration. The difference lies in pattern and control, and 3 Atlas continues to occupy a region where patterns appear unusually refined. This does not prove that 3 Atlas is technological, but it keeps the possibility open because nature rarely optimizes behavior without consequence. As analysis moves forward, 3 Atlas stands as a test case for interpretation itself. Whether the activity arises from natural sublimation or engineered exhaust, the behavior of 3 Atlas challenges observers to reconsider how motion, mass, and purpose are inferred from a distance. The limits of data transmission created an invisible boundary around what could be confidently said about 3I Atlas during its most revealing phases. Spacecraft and ground-based observatories gathered enormous volumes of raw information, yet only a fraction of that data could be transmitted, processed and contextualized in real time. This gap mattered because 3I Atlas was changing fastest precisely when observational bandwidth was most constrained. The JUICE spacecraft, while well positioned to observe 3I Atlas, was not configured for high-rate data return during that stage of its mission. Thermal constraints and antenna orientation reduced transmission speed, forcing engineers to prioritize navigation and system safety over continuous scientific output. As a result, many details about 3I Atlas remained stored on board inaccessible during the period when interpretation was most urgent. Ground-based telescopes faced a different limitation because atmospheric interference and scheduling constraints fragmented observation windows. Even when 3I Atlas was visible, long gaps separated high-resolution measurements, leaving analysts to interpolate behavior rather than observe it directly. These interpolations assumed continuity, yet continuity is precisely what 3I Atlas had begun to challenge. The consequence was not ignorance, but uncertainty structured by absence. Scientists knew where 3I Atlas was and how bright 3I Atlas appeared, but they lacked uninterrupted records of how activity evolved minute by minute. In physics, missing intervals matter because transitions often occur quietly, between snapshots rather than during them. This created an interpretive asymmetry, where models filled gaps with the most conservative assumptions available. For 3I Atlas, that meant favouring natural explanations, not because they were fully supported, but because alternative interpretations required details that were temporarily unreachable. The object existed in a space defined as much by what was not observed as by what was. Emotionally, this limitation introduced restraint rather than fear. 3I Atlas was not hiding behind secrecy, but behind the practical limits of human instrumentation. Yet those limits shape the narrative because incomplete data encourages coherence, even when reality may be uneven. As more data slowly returned, analysts became aware that early conclusions rested on partial visibility. The gaps did not invalidate observations of 3I Atlas, but they weakened the confidence with which patterns could be declared final. Every missing hour represented a potential change in behavior that went unrecorded. In this context, 3I Atlas became a lesson in how observation itself influences interpretation. The object moved through regions of space faster than data could flow back to Earth, creating a lag between reality and understanding. That lag formed a quiet void in the analysis, reminding observers that certainty often depends less on what is seen than on what is continuously seen. The search for radio emissions from 3I Atlas introduced a different kind of evidence, one defined less by presence than by threshold. Radio telescopes surveyed the region around 3I Atlas, not expecting a message, but seeking to establish whether any emission exceeded the background noise of the sky. What emerged from these observations was not silence, but a limit because 3I Atlas did not broadcast strongly enough to stand out clearly against cosmic interference. Arrays scanning the relevant frequencies recorded millions of signals, most of which could be traced to known sources such as satellites, terrestrial transmitters, and natural astrophysical noise. After systematic filtering, only a small number of unresolved signals remained associated with the direction of 3I Atlas. Those signals were weak, inconsistent, and ultimately dismissed as statistically insignificant, yet the dismissal itself revealed something subtle. By setting an upper bound on detectable emission, researchers constrained how loud 3I Atlas could be, if it were transmitting at all. The analysis suggested that any radio output from 3I Atlas would fall within the range of tens to 100 watts, comparable to a household light bulb rather than a planetary beacon. This finding reassured many observers because powerful transmitters would have been easier to identify and harder to ignore. However, low power does not necessarily imply irrelevance. In communication systems, power is often traded for directionality because a focused signal can carry information efficiently without flooding space with energy. If 3I Atlas were emitting narrow or intermittent bursts, those signals could evade detection unless the receiver happened to be precisely aligned. 3I Atlas therefore occupied an ambiguous radio space, neither demonstrably silent nor convincingly communicative. Natural processes can generate weak radio emissions, especially in environments shaped by plasma interactions and charged particles. At the same time, technological systems designed to conserve energy or avoid attention might operate within similar limits. Emotionally, the radio search produced calm rather than alarm because nothing resembling an intentional broadcast was identified. Yet calm did not equate to closure, because absence of strong signals only defined what 3i Atlas was not doing, not what 3i Atlas might be capable of. The low-power ceiling became a boundary condition rather than an answer. As the object continued its trajectory, attention shifted from whether 3 Atlas was speaking to, whether 3 Atlas was listening or relaying. Weak emissions could be sufficient for short-range communication, especially near massive planetary environments, rich in electromagnetic structure. This possibility reframed radio silence not as emptiness, but as selectivity. In the end, the radio observations added another layer to the portrait of 3 Atlas, one shaped by limits rather than detections. 3 Atlas remained quiet in a way that fit both natural restraint and engineered efficiency. The whispers, whether real or statistical, reinforced the broader pattern, because 3 Atlas continued to interact with observation itself, at the very edge of what could be confirmed. The approach of 3 Atlas toward Jupiter introduced a moment where geometry, timing, and probability converged with unusual precision. Jupiter is not merely a large planet because Jupiter dominates the gravitational architecture of the solar system and reshapes trajectories long before objects come close. For 3 Atlas to pass Jupiter at a distance of roughly 53 million kilometers required a path that was neither accidental nor forgiving. This maneuver is often described as threading the needle because the window for such a flyby is narrow when measured against interplanetary scales. A slight deviation earlier in the journey would have sent 3i Atlas far from Jupiter's influence or too deep into it, resulting in a dramatically different outcome. Instead, 3 Atlas arrived at the correct place and timed to receive a precise gravitational interaction without disruption. In celestial mechanics, gravity assists are common, yet they usually benefit spacecraft designed to exploit them. Natural objects experience them as well, but the probability of a small interstellar body encountering Jupiter at such a tuned distance is low. 3 Atlas therefore appeared to move through a corridor shaped by calculation rather than chance. The significance of this passage lies not only in proximity but in consequence. Jupiter's gravity alters velocity vectors, and even modest changes can define where an object will go for thousands of years. For 3 Atlas, the Jupiter encounter refined an already fast trajectory, accelerating its exit from the inner solar system. This refinement invites a deeper question, because if 3 Atlas was simply drifting earlier, uncertainties would have amplified by the time Jupiter was reached. Instead, the path remained coherent as though deviations were continuously corrected long before the encounter occurred. 3. Atlas reached Jupiter with its geometry intact, carrying forward the same balance that defined its earlier silence. Emotion enters quietly here because threading the needle does not feel dramatic in motion, yet it carries the weight of inevitability. 3. Atlas did not rush or hesitate, but passed Jupiter as though the encounter had always been part of its design space. Observers were left with the impression that the flyby was not a test but a confirmation. Whether driven by natural dynamics or something more structured, the Jupiter passage transformed 3 Atlas from a visitor into a traveller with intent. The object did not linger, yet it extracted exactly what Jupiter could offer, leaving behind a trajectory sharpened rather than altered. As 3 Atlas moved onward, the flyby stood as a moment where improbability narrowed into alignment. By threading the gravitational needle of Jupiter, 3 Atlas demonstrated that its journey was not defined solely by where it had come from. The encounter suggested that where 3 Atlas was going mattered just as much, and that direction was being maintained with remarkable discipline. Non-gravitational acceleration returned to the centre of discussion, as 3 Atlas departed the inner solar system with a trajectory that remained unusually clean. At this stage, the question was no longer whether extra forces acted on 3i Atlas, but whether those forces were the byproduct of chance or the result of ongoing control. Non-gravitational motion can arise naturally, yet the context in which 3i Atlas exhibited it complicated that explanation. In typical comets, non-gravitational acceleration fluctuates as jets activate and fade, producing subtle but detectable irregularities. 3 Atlas, however, displayed acceleration that was smooth, persistent, and aligned with long-term trajectory goals rather than short-term thermal changes. This consistency reduced the likelihood that random sublimation alone was shaping the motion of 3 Atlas. Luck remains a possible explanation because celestial mechanics can amplify small coincidences into large outcomes over time. 3i Atlas could, in principle, be experiencing a rare alignment of jet activity, surface geometry, and solar exposure that produces stable acceleration. Yet the probability of such alignment persisting across multiple observational phases is difficult to ignore. If non-gravitational acceleration were merely accidental, the effects would likely compound into detectable drift. Instead, 3i Atlas maintained a trajectory that preserved earlier assumptions while accommodating later corrections. This balance suggested feedback rather than randomness, even if that feedback operated within narrow margins. The concept of guidance does not require active propulsion in the traditional sense. 3i Atlas could respond passively to external forces while still achieving directional refinement, provided the structure of 3i Atlas constrained how those forces acted. Orientation, surface properties, and interaction with radiation can all shape motion without consuming large amounts of mass. From this perspective, the distinction between luck and control becomes blurred. 3i Atlas does not need to steer aggressively to achieve effective navigation, because small adjustments applied consistently can outperform sudden corrections. The path of 3i Atlas appears to reflect such cumulative influence rather than abrupt change. Emotionally, this realization introduces a quiet shift from surprise to contemplation. Observers are not confronted with evidence of maneuvering, yet observers cannot dismiss the elegance with which 3i Atlas maintains direction. The object moves as though guided by constraints that favor stability over efficiency. As 3i Atlas continues outward, the debate remains unresolved. Non-gravitational acceleration can be framed as fortune stretched thin or intention expressed softly. 3i Atlas occupies the narrow space between those interpretations, where motion alone cannot reveal motive but where pattern resists being called accidental. Jupiter enters the story of 3i Atlas not only as a source of gravity, but as a vast electromagnetic structure embedded in the fabric of the solar system. The planet's magnetic field is the largest and most powerful in the Sun's domain, extending millions of kilometers into space and interacting constantly with charged particles. When 3i Atlas passed through this region, it entered an environment where energy, motion, and information are naturally amplified. For spacecraft engineers, Jupiter is known as a natural laboratory for radio waves and plasma dynamics. Signals that would dissipate elsewhere can propagate, reflect, or intensify within Jupiter's magnetosphere. This property transforms the space around Jupiter into something resembling a relay zone rather than empty vacuum.